Thanks, Becca, and thanks organizer for inviting me, but somehow I couldn't attend because of some incident. So I'll be talking today small x physics at RHIC, Alice and EPIC. So this should be basically I'll show what RHIC has been done so far. Some results from STAR and Phoenix, and then I will go to Alice focal. I'll briefly describe what Alice is planning in proving gluon saturation, and then I'll show a few slides on what EIC is planning, and then I'll summarize. So gluon saturation been discussed long during this meeting. So I briefly say a few things so that we know already that gluon densities increases at low x. So this is an emergent phenomenon in all systems. In a state where this gluon density is increased such that the gluon splitting and these mixing they get balanced, and then we found a dynamic state where the proton density don't change, and we say that's a color glass condensate. And so we don't know exactly where this phenomenon when this state starts, and there is a scale we call saturation scale, which demarks the two regions, and to experimentally access this region, we need to have some moderate QSAT saturation scale, because in PP it's very low, so that it's very hard to get enough sensitivity there. So for that we move to nuclei, where the saturation scale is related to a power of A by 1/3. So here is a map in A and X, where a plane, it shows how the saturation scale may change and so in case of gold nuclei, we can see that even at 10 GeV square range, we can have a saturation regime. And one thing we have to remind from the kinematics, that if to reach the small x, we have to have very high rapidity to get access this regime. So here is X and Q square coverage shown for the RHIC in left hand side. So this is from 2007 long range plan or cold QCD plan for 2017 to 2013. So here at RHIC we see that this red one is the region demarcating where we may have the saturation region, and where we have detector in forward rapidity in the range around 3 units of rapidity. So that's what RHIC I tried to do during this time with two forward detector, one as at RHIC at STAR and one as at Phoenix. And if we see the acceptance in Alice, so we can see here the focal acceptance, which is a forward calorimeter with both electromagnetic and hadronic path. So that covers almost a very small x in between around 10 to the power -5, and even below the 10 to the power 6, and we can have a relatively high saturation scale, and so it's very convenient there to get direct photons and jet measurements from focal and to probe the saturation regime. We also see here a region in yellow where the EIC indicates, and it's relatively low Q compared to focal, but however, it has very wide acceptance. So now coming to few results from STAR and Phoenix. So in STAR, I would mention here that the first is forward detector, which we name called forward meson spectrometer. So it's an electromagnetic calorimeter covering a rapidity between 2.5 to 4. So this detector was supposed to detect photons and reconstruct pi 0 eta from those measured photons. And a detector in the similar rapidity in Phoenix, but in both sides. So this is called muon piston calorimeter. So these two detectors can probe small x because of their they are in the very forward rapidity. So the observable first we could think of these dihadron correlations or jet-jet correlations, where a parton when traversing through the dilute dense gluon field and then interact coherently, and they can diffuse and the width these get widened, and also the yield get suppressed. So that's what's been shown in this paper. And in the measurements, this Phoenix, where they have measured these dihadron correlations in PP and also in Digold systems for different centralities. So there, what they have observed the suppression of the Abhay peak, and it is more in case of Digold in central collisions. So if we see another results where they have defined the X and they're termed as fragmentation, because they are taking to final state particle, not the full jets partonic informations, and from their rapidity and PT information, they can have a sense of X, and with this X, they have plotted this JDA. So this is the ratio of the cross section of Digold to cross section of PP scaled by the number of collisions. And what they have seen that for these open markers in the Digold in one side, so there is no suppression, but at small x for the other side they have suppression. So so these are some results, but need to understand and the effect of multi-particle interaction. So this is not very unique in determining the saturation scale. And so STAR had in 2002 results in these pi zero correlations from this forward FMS, forward meson spectrometer, is that they have measured these delta phi correlations with a trigger particle from this detector piezo reconstructed in the region between 2 to 2.5 and an associated particle from 1 to 1.5. So they have observed the suppression for larger mass. So what's been seen that for P gold is more suppressed compared to P aluminum than PP. However, one thing is not observed, that the broadening. So from the picture of dilute dense picture, so when a large Spartan get coherent scattering. So one expect both yield suppression and angular decorrelations. So that's still it's not well understood why we don't see the change in we don't see the angular decorrelations. So while probing the gluon saturation, so there are different ways people have tried. So sorry, one example here is the transverse single spin asymmetry. So what we know this transverse single spin asymmetry, the left-right asymmetry. So they are non-zero in PP collisions, and there are papers where they have explained that in case of Pigul's gold system, then they would scale depending on the saturation scale. So in case of large nuclei, so this e to the power 1/3 factor would go inside, and we see the change in the single spin asymmetry while seeing the ratio. So from Phoenix measurements, the single spin asymmetry, they have find clearly that in case of PP, P aluminum, and P gold, there is a trend of decrease in these asymmetries. And in case of large nuclei, they are also split it into different centralities, and have seen a similar trend. However, the star measurements in pi zeros asymmetry. So these Phoenix measurements were charge hadrons. So there we expect not they would behave similarly with pi zero. However, star haven't seen such level of a drop in the asymmetry in large nuclei. So so far what we are seeing, there are measurements in single spin asymmetries, but not very conclusive. So there is also other effort in understanding the small systems in terms of initial state or color glass condensate. So we have seen in the talk earlier talks that the RHIC type of structure, these long range correlations. So these long range correlations in PP systems are not very well understood large multiplicity events. So in Atlas, they tried to explain these Atlas data with this paper. Raju and Dasling, they tried with Glasma model. And so the idea is that the correlation might be started from the initial state where the glasma itself responsible for such correlations. So there are several measurements in Phoenix, and I am not going in details. However, they tried to measure V2 and other flow dynamics. And for what they conclude from this 2017 paper, that we observe an imperfect scaling in V2 with eccentricity, so E2, so well reproduced by hydrodynamics, and this provide a strong evidence for initial geometry as a source of final state momentum anisotropy in this system. So they tried to say that initial state momentum or glasma is not responsible for such a state. However, still, I think this topic is very active since we have seen that Atlas results, they in PP, they are not understood in terms of these dynamics. So if now I shift from the results which I've shown to the Alice. So this Alice, what I'll show here, Alice. So based on this Alice public note to public notes. So in Alice, they have this forward forward calorimeter. So this consists of electromagnetic and hadronic path, and this coverage a wide rapidity of pseudo rapid range 3.2 to 5.8 and full azimuth, and it sits at 7 meter from the interaction points. And this focal electromagnetic calorimeter is a silicon and tungsten sampling calorimeter. So there are 18 pad layers and 2 pixel layers, 12 pad maps. And hello. Okay. So so this focal
Ganga, we still hear you well. No
okay.
problem.
So focal hadronic calorimeter is behind this focal electromagnetic. So this that is spaghetti type and scintillating fibers calorimeter. So energy resolution for focal electromagnetic is less than 4% at high energy. So this detector measures in isolated, inclusive and isolated photons. Sorry. Detected photons, and so we can also reconstruct jets and reconstruct pi zero from the photons measured, and also we can have JPSI and psi 2s states. So that is interesting for EPC physics. And I mentioned with Shuddha and Lokesh also mentioned that India is involved in hardware silicon pad, and they are responsible for 1/3 of the pad layer production. And I mentioned briefly how we detect direct photons here. So basically, when we see the energy around a cluster or photon detected, we sum up energy within some radius, and so we call it isolated PT, and that's summed over for both hadronic and electromagnetic calorimeter. And we see this red one falls very sharply in case of signals, and for background we see it's more extended. So based on these different nature, we can put isolation criteria and select events where which is responsible for direct photons, and in other than these isolation cut, we also put sour safeguard. So based on the hits on the pad layers and pixels, we can have these sigma longitudinal for signal and background. And also we put invariant mask cut. So based on these 3 cut, we can enhance the signal fraction by a factor of 11, and so we highly suppress the hadronic background. And we here one measurements we show for these RPA for direct photons, and they are these focal pseudo data. They are in the black dots, and if we see the impact of this focal data on these NNPDF feeds, so if there is no LSCB D0 data, so we see very wide patch. So this PDF is not very well constrained. But if we have LSCB D0, then we see it's very well constrained. So without with focal, we can have similar type of constraint on this NNPDF. So that shows in red. So that's the power here for these measurements of direct photon. And one correlations I'll show here, these direct photons and pi zero correlations. which we have measured. So we have these photons isolated and other criteria used to select photons, and then pi 0 is reconstructed from this detector. And when we make this correlation, we see these black correlations, and this is demonstration that we can do unfolding here and match these particle and detector level correlations very well. So one things I'll show while talking of precision measurements of the width. So we already discussed that in star that we see these yield suppressions in case in measuring these pi 0 correlations, but the width we haven't seen any sensitivity in the width. But in Alice focal, we can measure the width in very precisely, even in case of these rare correlations like gamma pi 0 correlations. And here is a statistical precision shown here, this relative error in different PT trigger and associated beams. And we see here that we can measure the width with the uncertainty of 0.001 radian in run for integrated luminosities. So I'll mention one topic here is vector measurements production in UPCA. So these focal can reconstruct Zephyr and size 2S state in Pilate collisions. So so these GEPSI current proto production, so in late collision, this can be extended up to 5.5 units of rapidity. And this W gamma for in the energy range is about 10 GeV. So these are overlapped with these experiments. So here once a few plots showing for these numbers of GEPSI and psi 2S states are generated for 7 nanovan inverse in these two plots. So and also here these transverse momentum distributions for cluster pair with this invariant mass interval. So I think Alice, I mentioned very few topics here, which from focal. So I haven't mentioned here jets. So so one capability of focal is also jet, since it has both hadronic and electromagnetic part. So we can do very well their jet physics and gamma jet correlations or gamma pi 0 correlations, and also and in UPC, JPSHI and difference these size states. So these are very promising for improving saturation physics. So now, while coming to EIC, so there are some advantages compared to what Alice focal can do. So Alice would come around 2029. And one thing in Alice is that it is large enough. We expect the saturation scale to be large, much higher. And in that case, these jets and direct photons, those are would be relevant there very. And however, in EIC, we know the kinematics very well defined, and we can define different type of events or different very more clearly. And we see here this saturation scale might be for root S 90 GeV between 1 to 2.5 GeV. So still it's accessible. And though while talking about jets at EIC is very shaky, because it's like the energy of this jet might not be that high, or the multiplicity. So we have to think of better way to identify or saying it's jets when doing jets physics and saturation at EIC. So here for this similar type of measurements, what we have discussed in PA or PP. So in these dihadron correlations is also holds here. We can also measure. And here one plot is showing here these correlation functions with saturation and no saturations model. So we see significant change in the yield and also width, even at 1 femto 1 inverse luminosity. And also we in Phoenix, while I showed Phoenix result, we discussed about this some term J, and also we can measure in case of EA. So here these two scenario where there is no saturation scale in blue and saturation scale in red. So this is for integrated luminosity 10 inverse femto 1. And so we see very overlap between these PA and EA collisions. And however, I think we have more precise control in EA collisions. So I'll show one of more slides. So measurements of diffractive events. So here, so diffractive events are very sensitive to the underlying gluon distributions, and this ratio of this cross section with gold to EP. We see here very distinctly these two model, one saturation model and shadowing model, they behave very different way. So I think these are very promising that we can measure at EIC. And I think nowadays there are a lot of work is been going on jets. These dipole while interacting with this dilute gold medium. So there are different papers where they have approached in jet terminology. So like diffractive dijet productions or in exclusive disobservables, and also these photon dijet or digest production in semi-inclusive observable, and also there are papers on back-to-back digest. So these are very interesting, but however, we need to understand what jet means in this low energy scale and its substructure. So as I mentioned, these energy and multiplicity is very low here. And in summary, I think this brings me summary. So we have studied this gluon saturation phenomenon and try to measure in different ways in stars and Phoenix. And so in Alice, but there is no very clear evidence that we have any hints of gluon saturation or the scale. So in comparison, Alice focal can go very small x 10 to the power -5, and relatively a hard region where we can probe saturation. So direct photons and jets are very promising there. And at EIC, this a precision machine that can probe gluon saturation in a very clean way and with very well-defined kinematic observable and different type of interactions. So that's, thank you. So
Thank you very much, Mriganka, for this very detailed talk. So any questions for Mriganka?
Hello, Mriganka.
yeah.
Yeah, so when you showed your results for the small systems, you mentioned that it is now the data for P2 is consistent with hydro and initial state geometry. So
this paper, what they have Phoenix, they have sent, they have mentioned, they tried to explain here that they can explain with hydro. Okay, so they disfavor other explanations based on initial state momentum space domain effect. So that's what they're telling here.
But these are very anisotropic systems, so they should have very strong like viscosities and also. And it is a few years ago. So then all these viscosity calculations were not under control, I guess. So what did they take in these calculations? Did they take the bulk viscosities also, or only the shear?
That I probably not don't know in the depth what calculation they have made. So yeah, so they have probably used they have of course used hydro and some model definitely, but yeah, it need to explore a bit more details what they have done.
Okay, thanks.
Any other question? Then I have one, or I have actually a comment. Mriganka, if you go to this new star data on the dihadrons, please, if you would be so kind.
This one?
Yeah. So you say we don't understand why we don't see broadening. That is not completely true. We understand very well. It is true that the CGC actually predicts broadening, but already in the EIC paper, we have shown that actually this broadening, which is comes from the TMD, gluon TMD, and it is a KT distribution, which is, as you write here, also sensitive to the saturation scale. The difference actually, if you have saturation, is in KT is relatively small between PP and P gold, but you have a lot of contribution from fragmentation and radiation, and that actually washes out the broadening effects. And we have Monte Carlo's studies and so on where we showed this. So to show this broadening will be difficult for anybody.
Okay, so means this fragmentation of some Sudoku factor was washing out.
It washes this out, exactly.
So that means the dihadron might not be the correct observable to.
No, because the suppression of the yield is extremely strong. But the broadening is just something which is very difficult to measure experimentally.
Okay.
And also these predictions for the dihadrons have not been done in NLO, and as such, some of that effects were not included.
Okay.
Okay. If not, then let's thank Mriganka again.